I'd like to thank the organizers for this nice invitation. And now, the swap. This is not a quantum operation, very classical, but it's a swap. That was a joke.
Very good.
Thank you. Okay, sorry about that. All right. So, anyway, so first of all, I'd like to again thank the organizers for this great invitation. And I haven't changed the title. It's a long title. I'm sorry about that. But again, the system that I will be talking about is very similar to some of the systems that were presented before, in the sense that these molecules are quite exotic. They are very extended and kind of a bit strange in that respect. So I will quickly give you an introduction and motivations, or at least from my point of view, why I find those systems interesting. I will talk about the long-range interactions and their behavior. I'll then talk about some older results that we observed, the Yukon group observed, and we were involved in the interpretation. And then I'll spend the end of the talk to talk about bound state and their properties in some calculations of spectra for macrodimers. And then next steps, conclusions, we'll see. All right. So we'll see that many of those topics are being touched during this workshop, and it really shows why this topic is interesting. It is ultra-cold Rydbergs are linked to cold plasmas, and can also be useful for quantum control of wave packets. It'll also be linked to this interest because of the anti-hydrogen experiments. There's also been talks already about many-body physics, and also there'll be more talks about quantum informations, and in particular for phase gates, sorry, and how the system behaves when you have mesoscopic samples. And again, one of the reason that we've seen now in the last few talks, and maybe even earlier, because I missed some of the earlier talks, there's a possible, not only possible, the detected trilobite-like Rydberg molecules, the macrodimers, and I think Jean-Michel talked about trimers as well. So who knows, this is growing. So the reason why I am interested in that, of course, started from the early work on quantum, the possibility of doing quantum gates with Rydberg. And there were the possibility of having a dipole blockade, and therefore this could be used to control the interactions and then do a phase gate with that. And then, of course, this blockade was observed at first a long time ago at Yukon, which was a van der Waals blockade. So when you have a big sample that you shine light on it, instead of having just a straight line, if you want, at low laser intensity enough, you would get a quick, rapid saturation that would correspond to locally having a domain of atoms that would be blocked from the excitations by other Rydberg atoms. As I mentioned, this was observed a while back, also by the group at Yukon, but also by the group of Matthias, the chair. So that allows me 2 more minutes, at least. So another reason why I find that system very interesting is that it could lead to the formation of Rydberg molecules. So usually a Rydberg molecule, one would think that you take a molecule and you take one electron, so you have a very tight core and one electron being excited around. There were, of course, proposal, and now has been observed, of systems where actually the two components are pretty far apart. One of them is excited, and the electron scatters off the other. These are the so-called trilobite or butterfly states that Chris Green and Hossein Sadeghpour and Dickinson, and also after that Fabricant and others worked on at some point. And those have been now also observed by Tillman, some version of it. And there's also the possibility of having those trimers, those Borel-mean states that Jean-Michel talked about. Those are also quite very interesting. Those are all very exotic and interesting states of that Rydberg systems can provide. So, as I mentioned, but this is now old news because they've been mentioned quite a lot already. The trilobite-like molecules have been observed in Rydberg by Tillman and his group, and basically they were at the time anyway observation of some of the bound states there. And also from the previous speaker, Jim, who saw macrodimer. I said like, but it's probably macrodimer, I should just say, molecules in cesium by the time of flight in an electric field. This was the topic of the previous talk, so I won't go in more details in that. So what I'm going to mention is when you have actually two Rydberg atoms and they interact at large distance. So the type of interactions you have will be, for example, van der Waals-like, that goes like scales like n to the power 11, and that is the scaling with which is a rapid scaling with n. And you can have also other power laws like C8, etc. And those can be positive or negative, because with Rydberg it all depends on the proximity of the nearest nearby states. And what you find is that well, a while back we predicted that there could be an attractive long range and a repulsive shorter range interaction that would give you long range wells. This was pretty schematic and a bit naive in the sense that there's many interactions that were not included in those estimates, but nonetheless it gave us the tools, or at least the taste to go further with that type of system. So, based on those type of curves, we were able to help interpreting some of the results at UConn. So this is a signal near 70p for Rydberg in rubidium, and there were little blips there, and that little blip did correspond very well to this asymptote. And from those simple curves with van der Waals coefficients only, you were able to find that, oh well, this could correspond to one of the curves coming here and cutting there. That was, of course, a bit simple as an interpretation, but nonetheless, it gives you it gave you a flavor of the physics involved. These little blips were observed for many n, and were a large distance, and they did scale the position scale like n cube, 1 over n cube, which is what is expected from how the asymptotes are moving with n. And it was quadratic in intensity, which implied it was 2 photon or 2 atom effect. And it agrees well in quotes with our curves, because those were the simplest curves at the time. So in order to take into account a bit more rigorously the interactions, what we needed to do is actually to take into account the coupling, the fine structure coupling, etc., and diagonalize and then find the exact, the right NL character, if you want, in it, right L character, and then convolve with the laser line width to get a spectra. So starting from those simple curves, we would actually add up the fine structure and start diagonalizing the various interactions between the different asymptotes, and we would be able to get something that would agree with these profiles. So this is a spectrum, a measured spectrum, and we're focusing our efforts on this little one here. So for that little one, these are the various curves that were relevant. So this is the dark blue is the asymptote where the little, corresponding to this little blip, And those other curves there are the nearby curve that mixes with it. So, and at the bottom here, as a function of the separation, this is the P character that you had in those wells. Basically, you needed to have the right P character to be able to make the transition. And you had, our approach was very simple. We just used molecular symmetries for the excitation, and we could find that there were basically 3 symmetries that were contributing. So this is one example. This is one U, and we have others. And when you put them together, and we solve it as a function of a time-dependent problem, and we have the contribution of three different symmetries. So you get the red one, which is a 0 G plus, the blue one, and the green one. Add them up together. This is what you get. This is as a function of the detuning. So you are going from the 2 atoms in the ground state to this molecular state, to a given molecular state. And by doing that, we were able to get a fairly good agreement with the experiment. So this is just a zoom around this little blip, and the red curve was the theory, and the dark curve the experiment. Of course, we had some arbitrary scaling of the theory curve, but the position and the shape was in pretty good agreement. That gave us some confidence that we were maybe be able to do something better for other molecular resonance. So we went back to this old friend there, and we started to look at the potential curves that we would obtain. And there, as you can see, as a function again of the separation, the situation is a bit more complex than this simple picture. What you can see something coming down like that, which is reminiscent of this curve, but it's much more complex. And here it's the equivalent of the P character that we had for the other curves, but it's just more complex because you have more curves that you can go to. And again, we have 3 different symmetries. So we have this one, and this one. It's also spaghetti-like, not as much as Jim's results, but they're pretty much there. So again, you have a lot of curve crossing and L mixing, if you want. And when you put all those contributions together, you obtain 3 contribution to a whole signal. So this is again the probability of exciting as a function of the separation, and the total had this shape. And when you integrate that, this is what you were obtaining. So as a function of the detuning from the P excitation, you would obtain different curves that you would actually compare with the experimental curve, and we could get a fairly good agreement. So all that gave us very good beside a very good feeling, gave us confidence in our potential curves. So we were able to match the position, and as a function of n, the scaling, the various scaling, this is a detuning, which scaled experimentally, and this is the dashed line is the expected scaling of the position, but also the size of that signal. We did calculations to try to estimate that size, and the scaling was n to the 8.5. And well, you could argue that this is a good or not, but it's in the right neighborhood. So these are the size of the 3 experimental signal there. Of course, here it's hard to really know what is the exact size, but these are the size that were extracted from these curves. So we get a fairly good agreement. Now, to come back to those curves, as I mentioned, the good agreement with the line shapes that we were calculating and when compared to the experiment gave us some confidence in those potential curves. And you'll notice that these curves have a nice well here, for example. There's other wells, but this one is a very nice deep well. And if we just calculate this well for various value of n, this is what we get. This is for the black curve, which is 59S, 62S. This is the asymptote, if you want. And this is as a function of the position. This is the depth of the potential. This is a potential. And the red one is the asymptote 69S, 72S, and the blue one is when you go even higher. So what you observe, as you go higher, from your perspective, the well is moving outward and becoming shallower. And the scaling of the potential, well, the depth of the potential scales like 1/n cubed, which is what you expect from just the asymptote for Rydbergs. And the position of the equilibrium distance scale like n to the power 2.5. That is less obvious. You could expect a scaling like n squared just from the Schrödinger equation, but from the 2.5, we basically it depends where the things are kind of crossing, where this kind of crossing that you see there occurs. So now we have a very nice situation where we kind of understand the scaling, at least, of those curves. So the next thing we did is we checked if those potential curves were robust with respect to small electric field. So this is what we just had. So I put them in different color. The red one is the potential we're interested in. And actually the other colored curves are actually the curves that are somehow mixed up, or the states are mixed up with the red one. So what we did at first, we just put everything in with a small electric field. We assumed that the molecular symmetries were still valid, which is of course not true. But we started with those states and assumed that for a small field, that small perturbation that this approximation would still be valid. And then we just built the asymptotic molecular states with that. So we just got a bunch of coefficients that depend on the field F. And now at 0.3 volts per centimeters, you see that you get something, they are changed a little bit, but not too much. So at least the red potential curve is quite similar to the zero field value. The other guys changed a little bit, but not too much. So that gives us a feeling, if you want again, that the potential curves and the wells that you would detect or you would measure if you were going to do so would be robust against small variations of the electric field. So that's the first thing we did. After that, what we looked at is that those wells actually do support a lot of bound states. For example, you can see that this is about, if you look, this is about 1.5 gigahertz. So it's pretty deep. They are deeper than what Jim mentioned, which was, I don't remember the exact number, but it was, yeah. So those seems deeper, which gives the hope that maybe actually bound states there could be detected. So for example, for the deepest one, they are about 3 megahertz apart, the bound states. For the 69S, 72S, which was the green curve, those are about 1.5 megahertz. So one could hope to be able to detect those states. And there's many of them, by the way, as I mentioned. As Jim mentioned, this becomes a continuum very quickly. So you have a bunch of bound states, and then suddenly they become so tight to each other, so close to each other, it's a continuum. So this graph just shows the various contribution of the various NL character that are in this red curve. So this is as a function of the separation. This red curve I'm sorry, but it's not very visible because all the colors look almost the same. So this one coming here and then coming back here, for example, this is the 69S, 72S character in that potential. And then, as opposed to what we were expecting, which was like, well, this curve looks like it's a crossing with this yellow curve, like an inverted crossing almost, a mixing. Turns out that actually this curve is due mostly to mixing with those two, the blue, the green, and the magenta curve up there. That's what you see, that the magenta here, which is a 69p, 71p, is mixing very well, and then it comes back up here. And the green one, which is 70p 1/2 and 70p 3/2, is here. So you see that where this minimum is actually, which we see here, where the minimum is actually, you have a lot of contribution from the upper curves. It's not from the upper curves, from the states linked to the upper asymptotes. And it makes sense from, if you think in terms of the Van der Waals coefficient, the largest contribution comes from the states that are nearby, at the denominator. And those are the ones that are mixing mostly with that particular asymptote, for example. And therefore, this tells us, and this is supposed to be orange and not yellow, this tells us that actually you could, depending on where you are in that well, the wave function you would get there would have different electronic NL character in it. And therefore, if you would excite in the outer region here, you would get mostly this 69S, 72S character. But for deeper levels here, you could actually have some P characters to it, which could be an interesting way to produce those molecules. So the next step we looked at is, well, what are the kind of formation schemes that one could come up with? So for example, you could go from 5S to some state there, and then you use CW excitations to go there. You could go different and different P states. You could go maybe up and come back down, or you could think of going directly from the continuum because those wells have both P and S character mixed in them. So this would allow these kind of possible schemes. And then, of course, what would be interesting is to use a scheme that will allow you to have the smallest width so that you could detect those bound states. Because I think I passed it. I don't know if I passed that. We did also the estimate of the lifetimes of those states, of those bound states. And as Jim got also, we got that they were basically, for all purposes, limited by only the atomic lifetime. So we're finding that the predissociation that you would get out of that due to crossing with the other curve, with the crossing, sorry, I shouldn't do that, it's bad manners, to the crossing and the crossing here going down there, so you could think that you have some oscillations, and whoop, you go predissociate, that actually this predissociation would be very inefficient. And actually those bound states there would be limited mostly by the atomic lifetime. Okay. All right, so next thing is well, let's try to calculate a photosociation rate. So it's a 2-photon process. We want to go from our starting point being an asymptote, which is already excited, and then going 2 photon up to a vibrational level in that well. So the simple expression there, we just use the ground state or pseudo ground state. Is just you have this radial part plus the electronic part, and the same thing is true with this vibrational level, where you have its vibrational wave function and an electronic part. And for example, this could be 69S or 268 P3/2, so some asymptote below, and you want to go to the some vibrational level up there. For your electronic state of the vibrational level there, we'll have various characters. We'll have characters from as I said, from the various S and P mixed together, and that depends on the position R, which was one of the previous view graph. So with that in mind, we get that the transition moment, if you want, between your vibrational electronic state and the electronic state of the ground state would have this shape. Basically, will depend on this coefficient C, which is this mixing of the various asymptotes, electronic atomic states. So with that, this is the kind of spectra we get for the first lowest three. This is not to scale. This is just to illustrate where they are. So if you start from 69S, you would go up there. You could go to the P, which were mainly the 69P and 71P, or the 70P, 70P, which was the green one in the previous view graph. Well, and you see that this well, the minimum there is located here and here. So you see that those two guys are not exactly the same scale, but not too different. So this one will give you probably larger contribution than the green one, which is what we kind of observe for those calculations. So here there were many assumptions that I put under the rug, but I can discuss that in details if you want. But this is for the three lowest levels. So if you start from 69S, you would populate something with a P character in these bound levels, and you could go to basically those two. So the real signal will be a sum of both, because you would not be able to distinguish that. You go to something with a P character, and this is what you get. And if you start from a P, there you could go to something with S over there, which in this case is the 69S, 72S, or the 71S, 70S, which is the blue curve there. So those would give you contribution as well. And again, here you see that they're quite different in the sense that if you look where the minimum here is, the red one has much more, a larger transition moment. If you wanted the C coefficient would be larger than in the case of the blue case. And therefore, this is about, what is it, 80 times larger than this one. But again, they would be superimposed, so it would be impossible in a way to detect, differentiate between those two contributions. So you would put a laser there, victory. He did that sign. So therefore, you would have a signal that would include both contributions. So the next steps will be to be a bit more serious about the treatment, and would be to include to go higher in levels, and to include also to be able to get how this envelope for the spectra would look like. And also, one of the things we'd like to work on is the various detection schemes that one could use. One could think of trying to ionize those states, or maybe to deplete them. So you have you put them to that vibrational level, and then you pump them down, or you pump them to another state, and then that would deplete the population of Rydberg atoms, for example. And the last few view graphs are about other possibilities. So we looked at different asymptotes. For example, instead of going to a PP asymptotes, you go to somewhere near DD. So you get, again, a bunch of curves. And what we observed in this case, that things are a bit sharper. So you could get wells, but they're so sharp that I would, I don't know if I would trust those things here, because they are very, very sharp. And that means that we might have to introduce more contributions, more interactions there. We also looked at other asymptotes, symmetries, for the 3U symmetry, for example. And again, you see, again, as a function of the position, other very strong wells. This is basically here a small zoom of this region. 340. No, it's the inverse. This is a small zoom of this region, and you see that it becomes very complex very rapidly. So, overall, as I mentioned before, and as many people mentioned, ultra-cold Rydberg systems are forming a very rich system. It allows for quantum information, ultra-cold plasma, and many body physics to be studied. The long-range interaction will play a crucial role in all those systems between single atoms, but also in a mesoscopic system. And finally, the ultra-long-range molecules, or could be trilobite or macrodimers, are a very exciting field to play with. And there's many experimental efforts now underway, so I would say the future is bright. Before finishing, just want to thank the students who worked on that. Jovica, who is now with Jean-Michel, Nolan, who I'm not sure if he was supposed to come, I don't know if he came, and of course the senior people, Phil Gould and Ed Eiler at UConn, and funding from those two agencies. And I couldn't resist, sorry, Matthias, I had to put Mr. Rydberg. This is a long-standing comment that Matthias told me that he's tired of seeing that view graph, so I had to put it.
Thank you very much.